Hi guys, so this is video 1 of topic 3 where we ask the questions, how do atoms bond? In this first lesson we will be talking about ionic bond formation. Now you will see that I've highlighted the word ion. Now why have I highlighted that word? Because that is what ionic bond formation is all about. It's the bond formation. What are bonds? It's basically, you can think of attractive forces between different ions that form due to them having different charges. Now, I just want you to recall, how do ions form? Ions form by the loss or gain of electrons. So it's charged particles. If I've got a negative ion, it means the atom gained electrons to become a negative ion, which we call an anion. Whilst if it's a positive ion, the atom lost electrons to become positively charged, and now it has more protons than electrons. So let's fall into the topic. So in nature, we do not find atoms as single atoms, monoatomic. We find most of our elements in compounds. Okay, now why do they form compounds? It's because they are reactive, meaning they react with other substances. So even if there was a piece of magnesium that for some reason was unreactive, the moment it comes into contact with oxygen or with water, it will react with the water and it will form a compound like magnesium oxide or magnesium hydroxide. So therefore, most of our elements we don't find in their elemental form as single atoms. We find them in compounds. Now, what is a compound? A compound is a substance that cannot be separated into simpler components by physical methods. So in other words, I can't separate these compounds by sieving or crushing or filtering. I need a chemical reaction to get this element in its elemental form where it's as a single atom. Okay, so, and what's the problem is that chemical bonding requires a lot of energy to overcome. So before we can understand why chemical bonding takes place and why we mostly find atoms in compounds, we need to understand why atoms want to form chemical bonds. Now, we're going to look at an example. Here we've got our piece of magnesium and it's reacting with oxygen, and you will see it's very reactive. It's producing that bright white light. Whilst on the other side, in this flask over here, we still have a piece of magnesium, but now it's in a neon atmosphere. A neon is a noble gas, which we say is inert. So in other words, it doesn't undergo reactions. It doesn't react with the magnesium. Now, why is there a difference? That's the question we want to ask. So, to answer that question, we have to look at the electron structure of oxygen and neon. Because remember, it's the electrons that are responsible for the chemical reactions that elements will undergo. So if we look at the electron structure of an oxygen atom, and this is what we learned in the first topic we did this year in grade 10, we will see that oxygen has an electron configuration of 1s2, 2s2, 2p4. Okay? Now I want to remind you, the first energy level can contain a maximum of 2 electrons. The second energy level can contain 8 electrons. So in this case, in the second energy level, we've got 2 plus 4, which is 6. However, in the case of neon, we've got 2 plus 6, which is 8. So neon has a complete second energy level, whilst oxygen is missing 2 electrons. Now, it's that difference between the two which makes oxygen very reactive, whilst neon is completely happy to be on its own in a monatomic form. So, the tendency of atoms to react to obtain an electron structure that is similar to that of a noble gas, we call the octet rule. Now just remember, the octet rule is just a rule we've made, and it doesn't apply to all atoms and elements. Okay, so there are certain atoms of elements that do not adhere to the octet rule. But for our purposes this year, we will mostly be working with elements that adhere to the octet rule when they react. So what does the octet rule say? So they say it's a concept of chemical bonding theory. Okay, so in other words, it's a theory and it's a concept of that theory. So it's not in practice that you can observe electrons and see, oh, there's 8. Okay, remember, we can't see them, they're too small. So it is a theory we've developed to help us explain the behavior we observe. So that's based on the assumption that atoms tend to have either empty valence shells or full valence shells of 8 electrons. Now, what is a valence shell again? The valence shell is the outer shell of electrons. So to just illustrate it, to just make sure you're with me, guys, I just want to draw an atom over here. So let's assume this is our nucleus over there. And here is our first energy level. And this is our second energy level. And if we are going to represent, let's represent oxygen. So in the first energy level, it has 2 electrons spinning in opposite directions. I'm using those half arrows that we used when we drew the Aufbau diagrams. So just that you're familiar with that. Now in the second one, I've got 1, 2 of them are paired. And then I've got 3 that I'm going to put down on their own first. And then I'm going to pair the 1. Okay, so there's my electrons. Now these ones here, we call the inner electrons. So those are our inner electrons, and these ones in the outer energy level, those are our valence electrons. Okay, so what this octet rule says is that when we have atoms, they will either want to have 8 electrons in the outer shell, so oxygen will want to gain 2 more electrons so that it has a full outer shell, or it will lose all of its electrons in the outer shell. Now, if I, for example, drew lithium as well, so if we drew lithium, and that's the nucleus, and here I've got my first energy level, and there's my second energy level, lithium will have 3 electrons in total, so there's my first 2, and there's my third one. Now, that third one, lithium needs 7 to gain a full outer shell, or it will only have to lose 1. What is easier? I guess losing 1, eh? Let's see. So, our next section of work that we're talking about is the most reactive elements. Now, what are the most reactive elements we find on the periodic table? So, the elements we find on the periodic table that are most reactive are the ones in group 1 and the ones in group 17. So they're quite far away from one another. Now, why are they most reactive? That's our question. So let's take potassium as an example. Okay, so potassium is also in group 1, which means it has 1 valence electron like lithium. So in the case of potassium, it only needs to lose 1 electron to form a positive ion, or a cation that we specifically call it. Then it will have an empty valence shell, and the rest of its shells will be complete. The other option potassium has is gaining 7 electrons to gain a full outer shell. And like I said with the case with lithium, it's easier for potassium to lose that 1 electron. And therefore potassium, we know group 1 elements form ions with a charge of 1 plus by the loss of 1 electron. So if we look at the electron configuration of potassium, there is the 1 electron. It will lose that 1 electron to then have a full outer shell. And if it forms this potassium ion, it gains an electron configuration similar to that of the element argon, which is a noble gas. Now, previously we learned when we have atoms that form ions, they form ions so that they have electron configuration similar to that of the noble gases. So, potassium will lose 1. If we look at the other side to group 17, and we take chlorine as an example, chlorine has 17 electrons. So what does it need to do? If you look at the electron configuration, it has 5 electrons in the 3p orbital. So if it gains an additional electron, it will have 6 electrons in the p orbitals, and it will in total have 8 in its valence shell, therefore also giving it the same electron configuration to that of argon. So now we've got metals and non-metals both having the same electron configuration. But why do they do that? Okay, the reason here is that then they become more stable. So our non-metals will form anions and our metals will form cations. So metals form cations and non-metals form anions. Okay, why do non-metals form anions? Because it requires less energy to add electrons to non-metals to have a noble gas configuration than losing a lot of electrons. Chlorine will have to lose 7 electrons to gain a noble gas configuration, which is much more difficult than, or lose 7 electrons to gain a noble gas configuration, which is much more difficult than just gaining 1. And in the case of potassium, it only needs to lose 1 instead of gaining 7. Okay, now what is so special about these ions that form, guys? They are stable, okay, which means they don't need to react. So what happens? The parent potassium and chlorine atoms are very reactive. They want to react. However, the ions have chemical properties that are more like that of an atom of argon. Okay, so they become more stable. Chloride ions and potassium ions are much more stable. They behave much more like a noble gas atom does. Why? Because their electron configuration has changed. And remember, it's the electron configuration that's responsible for how an atom will react. Okay, now this is just a side note that you should take note of, because we're going to get to it later when we name different compounds, that we get certain atoms that don't have only one configuration of electrons when they form ions, and they also don't get noble gas configuration. And these are mostly our transition metals, which are in the middle of our periodic table, groups 3 to 12. An example of this is like copper. Copper can form a cation with a charge of 1 plus, or it can lose 2 electrons to form a cation with a charge of 2 plus. Both cations are stable, but none of them have noble gas configurations. That you will learn about later in chemistry if you continue with it in grade 11, 12, and onwards. So in summary, what do we need to know? How does an ionic bond form? An ionic bond is the bond formation where two oppositely charged ions attract one another. And if we have oppositely charged ions attracting one another, a positive and a negative charge, we call it an electrostatic force that is responsible for our ionic bond. So ionic bonding is the transfer of electrons and the subsequent electrostatic attraction. We will discuss another type of bond formation, which we call covalent bonding, in another lesson at a later time. So just to summarize what we've learned. So if we take our potassium and chlorine atoms as example, the potassium atom loses an electron to form a potassium ion. Okay, this electron can then be gained by a chlorine atom to produce a chloride ion. And now I've got a negatively charged ion and a positively charged ion. And these ions can bond in what we will learn later, we call a crystal lattice, where we've got many ions of potassium and chlorine, or chloride ions specifically then, that bond due to this opposite charges, which we call an electrostatic force. And that then is what we call an ionic bond. Now, it's important, guys, as we will discuss later, that ionic bonding never occurs just between one ion and another ion. It occurs between a number of ions in what we call a crystal lattice. At this point in time, I want you to review the lesson if there's anything that's unclear, and then you should complete the questions at the end of this lesson. Thank you, guys.